let us discuss anharmonic oscillator. The harmonic oscillator, which we learned in the last video lecture, is a model for the vibrating diatomic molecule. It is just an assumption. We applied Gaussian potential or harmonic potential to derive the expression for vibration energy. But in reality, anharmonic oscillator with the most potential function is used to obtain the vibration energy for any diatomic molecule. The potential energy curve of an anharmonic oscillator is not parabolic, but instead it is called as a Morse curve. An anharmonic oscillator is a system that deviates from harmonic oscillation where the restoring force is not proportional to the displacement. The theoretically obtained values using anharmonic model exactly match with the experimental values. The more intense lines is called as fundamental. The weak intense lines are known as overtones. Generally, a real molecule does not obey exactly the law of simple harmonic motion. The real bonds, although elastic, are not so homogeneous in order to obey Hooke's law. If the bond between atoms is stretched, there comes a point at which it will break, then the molecule dissociates into atoms. Thus, for small compression and extension, the bond may be taken as perfectly elastic. And for larger amplitude, greater than 10% of the bond length, a much more complicated behavior must be assumed. The following figure, in the next slide, the following figure shows the shape of the energy curve for a typical diatomic molecule. Together with dashed, we are going to look into the ideal simple harmonic parabola. A purely empirical expression which fits this curve to a good approximation was derived by P.M. Morse and is called as the Morse function. So this is and this graph shows that Morse potential, the Morse curve. The energy of a diatomic molecule undergoes anharmonic extension and compression. And green color shows the harmonic potential. This is just an approximation, which you have learnt already. And the energy levels are equally spaced. Whereas in reality, anharmonic oscillator exists, and it shows a blue color. See, the graph is drawn with a blue color, and this is the Morse function, Morse curve. And what is the spacing? The spacing is not even, and the spacing decreases as nu gets a greater value. So as nu increases, the spacing between these two levels, higher levels, decrease. And nu is nothing but the vibrational quantum number. And the highest energy is nothing but dissociation energy. Dissociation energy is the highest energy level. And here, D0 is the true energy, which is measured from the first level, nu equals 0. The graph has been drawn between energy and the internuclear separation of two atoms in a diatomic molecule. The Morse potential is drawn in a blue color, whereas the harmonic oscillator potential is drawn in green color. The energy levels of the harmonic oscillator potential are evenly spaced, but the energy levels of Morse potential are not evenly spaced. The energy levels of Morse potential decrease as the energy approaches the dissociation energy, which is the maximum energy. The dissociation energy dE is larger than the true energy D0, and this energy is required due to the 0 point energy of the lowest vibration level, nu equals 0. There is only a small correction from the ground state to the first excited state for the anharmonic correction, but it becomes much larger for more highly excited states which are populated as the temperature increases. So it depends on temperature too. The deviation from the harmonic oscillator to the anharmonic oscillator results in expanding the energy function with additional terms and treating these with perturbation theory. The results in the correct vibration energies when applied selection rules. The selection rules are del nu, which is equal to plus or minus 1. For weaker overtones, the selection rule is nothing but del u equal to plus or minus 2, plus or minus 3. For strong and more intense fundamental, the selection rule is del nu equals plus 1 or plus or minus 1. It should be noted that del nu equals to transition does not occur at twice the frequency of the fundamental transition, but at a lower frequency. The Morse potential is given as equation 2.12. E equals dq, where dq is nothing but the dissociation energy, the maximum energy. 1 minus e to the power a rq minus r whole squared, where a is a constant for a particular molecule. When equation 2.12 is used instead of equation 2.2, so this is 2.2, which we study for harmonic oscillator. So instead of this, if we use this equation 2.12 in Schrödinger wave equation, the expression of the allowed vibration energy levels is found to be this expression 2.13, and this is the first term and this is second term. Second term is a contribution from anharmonic oscillator. Suppose if there is no anharmonic oscillator, then the first term alone is this, which is nothing but the vibration energy levels for harmonic oscillator. And here omega bar E is nothing but oscillation frequency, that is equilibrium vibrational frequency, which is measured in centimeter power minus 1, and Xe. X is the corresponding anharmonic constant. What we call this as anharmonicity, which is always a small value and a positive value. It's around 0.01 positive value, so that the vibration levels are found to be more closely together with increasing nu. It should be mentioned that equation 2.12, so this is equation 2.12, and like 2.13 is an approximation only. So these are all approximation only. More precise expression for the energy levels require cubic and quadratic. So we'll have to go with more powers, etc. Terms in nu plus 1 by 2 with anharmonicity constants like A, B, C, and goes on. These terms are important only at larger values of nu, and we are going to ignore this in this derivation. So if you rewrite equation 2.13, so this is equation 2.13. For the anharmonic oscillator is given by this. See, we know already equation 2.13 is given as this. So this is equation 2.13, which I have written here. Now I can pull the common term out, nu plus 1 by 2. See here. So we have pulled nu plus 1 by 2 common out. The remaining terms we have written as E nu, which is nothing but the the vibrational energy level, which is equal to omega bar E 1 minus Xe times nu plus 1 by 2 multiplied by nu plus 1 by 2, and compare with the energy levels of the harmonic oscillator, equation 2.6. So this is for the harmonic oscillator, energy levels of a harmonic oscillator. Just we can compare this 2.14 with the 2.6. And of course, nu plus 1 by 2 is just equal to nu plus 1 by 2. The remaining term will be equal to omega bar oscillation. See, omega bar oscillator. See here, we have nu plus 1 by 2 in equation 2.6. And here in equation 2.14, we have again nu plus 1 by 2. You compare this equation with this equation, and we have the remaining term, omega bar oscillator is nothing but the remaining terms, which is given by this equation 2.15. And here, as nu increases, omega bar oscillator decreases. Thus, the harmonic oscillator behaves like a harmonic oscillator, but with an oscillation frequency which decreases steadily with the increasing nu. So your wave, this is energy, which is nothing but wave number, which is equal to omega bar E 1 minus xe mu plus 1 by 2 times mu plus 1 by 2. If you consider the hypothetical energy state obtained by putting nu equal to minus 1 by 2. So this is equation 2.15. You substitute nu equals minus 1 by 2, it gives 0. See, you just substitute here minus 1 by 2. Minus 1 by 2 plus 1 by 2, that will give us 0. The total expression becomes 0. What we call this is zero vibration energy. We are going to substitute nu equals 1 by 2. We get 0 vibration energy. This is just a hypothetical energy state. Similarly, when you are going to substitute here minus 1 by 2. So minus 1 by 2, that also will become 0, whereas omega oscillator, which is equal to, we have omega bar E. See here, minus 1 by 2 plus 1 by 2, if we substitute here, this becomes 0. So omega oscillator, which is equal to omega bar E. So this is given us equation 2.16. If you are going to substitute nu equals minus 1 by 2. Thus we see that omega E may be defined as the hypothetical equilibrium oscillation, as we have given nu equals minus 1 by 2. Frequency of the unharmonic system for the frequency of infinitely small vibration above the equilibrium point. For any real state specified by a positive integral nu, the oscillation frequency is given by, so which is nothing but for any ground state, nu equals 0, we can have this. We just substitute in equation 2.15, we have 2.15, you substitute nu equals 0 here. If you are going to substitute nu equals 0 here, we have the oscillation frequency, which is given by, instead of oscillation, you just substitute 0. So omega 0, which is equal to omega E 1 minus xe by 2, because you are going to substitute nu equals 0. And similarly, the energy, the vibration energy is given by this expression. You substitute nu equals 0 here, and we will have epsilon naught 1 by 2 omega bar E times 1 minus xe by 2, which is measured in terms of centimeter power minus 1. And we see that 0 point energy differs slightly from that for the harmonic oscillator, given as equation 2.8. So you just compare this equation. This is equation 2.8 with 2.18. You just compare this one, and this is for anharmonic oscillator, and this is for harmonic oscillator, and it differs only by means of 1 minus xe by 2. Xe is nothing but unharmonicity, unharmonic constant. The selection rules for the unharmonic oscillator are as follows. Del nu equals plus or minus 1, plus or minus 2, plus or minus 3, and goes on. Thus, they are the same as for the harmonic oscillator, with the additional possibility of larger jumps. These are all predicted by theory and observed in practice to be of rapidly diminishing probability, and normally the intensity of lines is observed only with del nu equals plus or minus 1, plus or minus 2, plus or minus 3, and so on at the most. Further, the spacing between the vibration levels is of order 10 to the power 3 centimeter power minus 1, and at room temperature we may use the Boltzmann distribution to show this one. And for the first excited state, so n nu which is equal to 1 divided by n nu which is equal to 0, which is equal to, this is our Boltz's distribution law, Boltz's distribution function. So we have e power minus 6.63 10 power minus 34 into 3 in 10 power 10 multiplied by, this is given as 10 to the power 3. So we are going to substitute here, we have substituted here, divided by Boltzmann constant 1.3 10 power minus 23 room temperature multiplied by 300. So the answer is 0.008. In other words, the population of nu equals 1, the first excited state, is nearly 0.01. in terms of percentage, this is 1% of the ground state population. Thus, it's a very good approximation. We may ignore all transitions originating at nu equals 1 or more and restrict ourselves to the 3 transitions. So we are going to look into 3 transitions, nu equals 0 to 1, 0 to 2, 0 to 3. Let us see how it goes. So first we'll go with nu from 0 to nu equals 1. What we call this is more intense line. And the difference between these two is nothing but plus 1. So del nu is nothing but plus 1. And the corresponding oscillation frequency one can calculate. So del E, which is equal to E nu equals 1 minus E nu equals 0. This is oscillation frequency. The oscillation frequency is given as this expression. See here, this is the expression, and we can pull out nu plus 1 by 2 here. See, we have pulled out nu plus 1 by 2. You just multiply this inside nu plus 1 by 2. We'll get this expression. So we are going to use this expression only. And of course, this is the expression, equation 2.14. You multiply nu plus 1 by 2 inside, and we will have omega E nu plus 1 by 2 minus omega E x E nu plus 1 by 2 whole square. So we are going to use this one only. And for the first transition, that is nu equals 0 to nu equal to 1. You substitute first nu equal to 1 here, and here also nu equal to 1. And that is for this value. And substitute the nu equal to 0 here, and nu equal to 0 here, and that is the second expression, second term. So we will have now nu equals 1. So this becomes 1 plus 1 by 2. As it is a number, we have brought front. So 1 plus 1 by 2 omega bar E minus the second term will be 1 plus 1 by 2. So 1 plus 1 by 2 whole square omega bar E x E minus then this expression for nu equals 0. So you substitute nu equals 0 here, we will get this. You substitute nu equal to 0, we will have this. 1 plus 1 by 2 is nothing but 3 by 2 omega bar E. And the next term will be 3 by 2 whole square, which is nothing but minus 9 by 4 omega E x E. And this term as it is like this, and this term is nothing but plus 1 by 4 omega E x E. Now, we just simplify the first term and third term. So this is 1.5 omega E, and this is half omega E. That will give us 1 omega E. And take the second term and fourth term. So this is the second term, and this will be a fourth term. Minus 9 by 4 plus 1 by 4 is nothing but 8 by 4. Minus 8, here minus is there. So minus 8 by 4, which is nothing but minus 2. So minus 2 omega bar E x E. And you pull omega E out, that will give us this expression, equation 2.21. Similarly, one can calculate the transition from 0 to 2. That is nu equals 0 to nu equals 2. And what are the intensity? So this will be weak intensity. Again, use this formula. You substitute nu equals 2 first. Then after that, we are going to substitute nu equals 0 and subtract. So we have now 2 plus, instead of nu, you substitute 2 here. So 2 plus 1 by 2 omega E minus x E, 2 plus 1 by 2 whole square omega E minus 1 by 2 omega E minus 1 by 2 whole square x E omega E. And this becomes 5 by 2, and this becomes 5 by 2 square, which is nothing but minus 25 by 4 omega E x E. And this term is minus 1 by 2 omega E. And this term we will have minus minus plus. So 1 by 4 omega E x E. As usual, first term and third term. So this is 2.5 and this is half. When you are going to subtract, answer will be 2. So 2 omega E. And this is 25 by 4. This is 1 by 4. So 24 by 4. That will give me 6. So 6 omega E 6E. You pull 2 omega E out. So we have 2 omega E 1 minus 3xe. And this is the difference in the frequency which is given by this expression 2.22. And let us go for the third one. Again, the intensity is very, very less. It's a weak intensity because it goes from 0 to 3. It jumps from 0 to 3, the transition line. So Again, we'll have to use the same formula. Here, for nu, we are going to substitute 3, and for the next one, nu equals 0. So we have 3 plus 1 by 2, and here also 3 plus 1 by 2 whole square, the remaining term as it is. And this will give me 7 by 2, and this will give me 7 by 2 whole square, which is nothing but 49 by 4, and this is as it is. Simplifying the first term and third term will give us 7 minus 1, 6 by 2, which is nothing but 3 omega e. And what is the second term and last term? Second term and last term will give us 49 by 4. Here it is plus 1 by 4. So the answer will be 48 by 4, which is nothing but 12. So minus 12. So pull 3 omega e out. That will give us 3 omega e 1 minus 4 xe centimeter power minus 1. These three transitions are shown in the figure, which we are going to see now in the next slide. To a good approximation, since xe is a positive quantity and also it's very, very less, 0.01, the three spectral lines lie very close to omega e, 2 omega e, and 3 omega e. The line near omega e is called as a fundamental absorption, and the rest of the things, what we call this as overtones, first overtone, second overtones, and goes on. For example, the spectrum of HCl shows a very intense absorption at 2886 centimeter power minus 1 and weaker at this frequency number and very weak at this frequency. And these are the lines. So from nu 0 to 1, very high intense line, and 0 to 2, somewhat less intense, 0 to 3, again still very less intense, very weak intense. Thus, we observe that for the ideal harmonic oscillator, the spectral absorption occurred exactly at the classical vibration frequency, and the equilibrium frequency may differ considerably. The force constant of the bond may be calculated directly by inserting the value of omega here. So in this expression, we can get K. If we know mu, the reduced mass of the system, and value of omega E, one can get the value for the force constant of the bond. When the fundamental constants and the reduced mass are inserted in the above expression, one can study the other diatomic molecules by infrared techniques. In addition, one can also study the transitions from nu equal to 1 to higher states, nu equal to 2. So this is nu equal to 1 to 2. Earlier we studied with nu equal to 0 to 1, 0 to 2, 0 to 3. Now this is nu equals 1 to 2 and similarly 1 to 3 also. What we call this as hot bands. We'll see later. But the intensity will be normally very, very weak. For example, we can study the transition from nu equal to 1 to 2. Use the same formula. You substitute for nu equals 2 here, and here it is nu equals 1. We have this equation, and this is nothing but 5 by 2. This is 5 by 2 whole square, and this will be 3 by 2 and 3 by 2 whole square. And first term and this term, third term. So 5 by 2 minus 3 by 2 will give us, this is 2.5, this is 1.5. The answer is 1. Minus with a minus sign, answer is 1. So this will become omega E. And minus 25 by 4, this is plus 9 by 4. 16 by 4, answer is 4. So minus 4 xe omega E. You pull omega E out, that will give us omega E times 1 minus 4 xe centimeter per minus 1. This weak absorption is found to be closer to our lower wave numbers than the fundamental, since xe is very, very small and positive. Such weak absorptions are called hot bands. So hot bands are jumps from one level to second level, one level to third level, first level to fourth level, goes on. Since a high temperature is needed for their occurrence, their nature may be confirmed by raising the temperature of the sample, when a true hot band will increase in intensity. Now we'll see the definitions for fundamental vibrations and overtones, which you have already studied earlier. We'll see the definition now. So fundamental vibrational frequencies of a molecule correspond to transition from nu equals 0 to nu equals 1. For a non-linear molecule, there will be 3n minus 6, where n is the number of atoms, number vibrations. For non-linear molecule, the formula is 3n minus 6. The same rule holds good for linear molecules. However, the equation is 3n minus 5. So for linear molecule, we are going to use 3n minus 5. Whereas for non-linear molecule, we are going to use 3n minus 6. Because a linear molecule has one less rotational degrees of freedom. The following figure, which you are going to see now, diagram for a vibrating diatomic molecule. The levels denoted by vibrational quantum numbers nu represent the potential energy for the harmonic, which is another quadratic oscillator. The transition 0 to 1 is the fundamental. The transition from 0 to n is greater than 1, are called overtones, like 0 to 2, 0 to 3, 0 to 4, and goes on. Whereas the transition from 1 to 2, 1 to 3, 1 to 4 are called hot bands, hot transitions. So as I said just now, and this is the figure, and 0 to 1 is nothing but fundamental 1, and 0 to 2 is nothing but first overtone, 0 to 3 nothing but second overtone. The transition from 0 to 4 is nothing but third overtone. And what of the level from 1 to 2, 1 to 3, 1 to 4, they are all called hot bands. And this diagram is a potential energy diagram for a vibrating diatomic molecule. Next, overtones. Overtones occur when a vibrational mode is excited from nu equals 0 to nu equal to 2, which is called the first overtone, or nu equals 0 to nu equal to 3 is the second overtone. The fundamental transition nu equals plus or minus 1 are the most commonly occurring, and the probability of overtones rapid decreases as nu increases. And nu equal to plus or minus 1 will have more intense. Other overtones will have weak intense. Based on the harmonic oscillator approximation, the energy of the overtone transition will be about n times the fundamental associated with that particular transition. The anharmonic oscillator calculations show that the overtones are usually less than the multiple of the fundamental frequency. Overtones are generally not detected in larger molecules. And this is the typical HCl vibrational spectrum. Look at the wave number. So it is around 3000. This vibration spectrum. This is infrared spectrum of hydrogen chloride. And look at the first column. And of course, the transition is fundamental 0 to 1, 0 to 2, 0 to 3. They are all overtones here. And these are all observed values. See, these are all observed values, experimental values. And the second column is using harmonic potential. And the third column is using anharmonic potential, which is nothing but Morse function, Morse curve. And look at this column and this column, the answer is almost the same. So look at the observed value, experimentally observed value, and this column exactly matches with the theoretically observed by anharmonic, using anharmonic function. So this is anharmonic oscillator. Combination bands. Combination bands are observed when more than 2 or more fundamental vibrations are excited simultaneously. One reason a combination band might occur if a fundamental vibration does not occur because of symmetry. This is comparable to fibronic coupling in electronic transitions, in which a fundamental mode can be excited and allowed as a doubly excited state. Combination implies addition of two frequencies. So addition of two frequencies is about combination bands. But it's also possible to have a difference band where the frequencies are subtracted. Hard bands. In the harmonic oscillator model, hard bands are not easily distinguished from fundamental transitions because the energy levels are equally spaced. Because the spacing between the energy levels in the anharmonic oscillator decrease with increasing vibration levels, the hard bands occur at lower frequencies than the fundamentals. Also, the transition moment integrals are slightly different since the ground state will not necessarily be totally symmetric since it is not in nu equals 0. Fermi resonance. Fermi resonance occurs in the splitting of two vibrational bands that have nearly same energy, same energy and symmetry in both IR and Raman spectroscopy. The two bands are usually a fundamental vibration and either an overtone or a combination band. The wave functions for the two resonant vibrations mix according to the harmonic oscillator approximation, and the result is a shift in frequency and a change in intensity in the spectrum. As a result, two strong bands are observed in the spectrum instead of the expected strong and weak bands. It is not possible to determine the contribution from each vibration because of the resulting mixed wave function. Now let us solve one problem. The fundamental and the first overtone transition of N14 O16 are centered at 1876.06 cm^-1 and 3724.20 cm^-1 respectively, and it is asked to evaluate the equilibrium vibration frequency, the anharmonicity, the exact 0-point energy, and the force constant of the molecule. So given that, and this is the fundamental one, and this is the first overtone frequency, and we know that the formula goes omega bar E 1 minus 2x is given as this value, and 2 omega E for the overtone, first overtone, is given as this expression. And of course, we know omega E is nothing but equilibrium vibration frequency in cm^-1, and x is nothing but anharmonicity, anharmonic constant. Now divide this equation, the first equation, by 2, that will give us 1/2. That will give us this expression. Cross multiplying will give this value. So when you are going to cross multiply, this multiplied by this and this multiplied by this will give this expression. Now the first term is multiplied by 1 will give this expression. The first value is multiplied by 2xe will give us this value, minus 7448.4xe. And this right hand side, this value is multiplied by 1 is as such like this. This value multiplied by 3 will be given as this. Now you bring xc on left hand side. So this term, the second term of the on the right hand side, you bring this term to left hand side and pull xc common out. So we will have this expression. And similarly, you can pull the first term in the left hand side to right hand side. You bring this term. And subtraction will give us 27.92, and this expression, this value is given as 3807.96. One can get the value of xe, which is nothing but 7.332 in 10 power minus 3. And x is nothing but anharmonicity, anharmonic constant. So we can also get the oscillation frequency. Substitute the value of xc here. Substitute the value of xc here. We can get omega e. Either way, either here or here, one can get the value of omega e, oscillation frequency, which is equal to 1903.96 cm^-1. Now we know the expression for 0-point energy is given by this 1/2 oscillation frequency times 1 minus xe by 2. Substitute the expression, all the values here. Substitute all the values here. We will have the 0-point energy is given as 948.5 cm^-1. Let us calculate now force constant. Force constant is expressed as 4 pi squared omega e squared c squared mu. We will have to go with the expression for mu, the reduced mass, which is given as m1 m2 divided by m1 plus m2, and m1 is given as this value, the mass of nitrogen 14 is given by this value, and mass of O16 is given by this value. Get the expression for mu, m1 m2 by m1 plus m2, substitute these values we know the reduced constant as 12.39 in 10 power minus 27 kgs. Substitute here. So substitute in this equation, we know the force constant value as 1596 Newton by meter.